view graphs. So these are some of the buzzwords. GNC, you should know what that is. Guidance, navigation, control. Navigation is PVT, position, velocity, and time. And we redefined those things technically last week so that you'd have an idea of how difficult sometimes it is to do some of these concepts that we think we have in our head. So for example, if we're talking about position, P, position, we've got two sources of position from aircraft sensors. The first one, of course, is GPS, or SV, space vehicle or GPS position. It's always the same. And what do you get your position from GPS? GPS knows nothing about the Earth's shape or where you want to go. It knows nothing. What does it know? It knows that the Earth is a mathematical ellipsoid, and it'll place you on the mathematical ellipsoid in what's called ECEF coordinates. That's how GPS works. So your cell phone or GPS receiver has to convert the mathematical ellipsoid position to where you are. And this has led to crises, deaths in some cases, of people who didn't follow the procedure, didn't understand exactly what they were doing when they're using GPS. The second, I should mention also that GPS is jammable. It's a radio. The GPS is a very, very low signal-to-noise ratio. It has very high noise content. So it's very easy to jam. Very easy to jam, and it's very easy to spoof, what do you call phishing, right, in the internet sense. It's very easy to hack, spoof, or filter. GPS became a civilian thing in the Clinton administration because it turned out to be so useful. It's actually a military system. So the military has precautions against spoofing and jamming, but the civilians don't. And we're already seeing this happen in the Black Sea, in the Middle East. I just read last week that they are jamming tankers. Ships are being jammed for hours and days at a time using GPS. And it's basically people who don't understand how the GPS works and why they should always have a backup. The other way that we can get position is from inertial navigation system. Those are little self-contained boxes, the size of my thumb basically now. They used to be shoebox-sized boxes when I was flying. An inertial navigation system has accelerometers and gyros, and it gives you your position. It's not jammable. It's totally self-contained, hack-free, hack-proof, jam-proof. It's passive. Nobody knows you're using it. And so almost all military aircraft have inertial navigation systems on them as a backup or in complementary with the GPS. So if you know your weapon, for example, is going to get jammed going into the target, which it always is, then your weapon will automatically switch to an INS at the end game. So how they talk to one another is very complicated, much beyond the scope of this class. But what I want you to remember is that the inertial navigation system uses the geoid. And the geoid is an Earth with just water on it. And where that water would settle would be MSL, mean sea level. And that turns out to be the height reference for the ellipsoid as well. So the height reference for the ellipsoid is the MSL determined by the geoid. And as you can imagine, it gets quite complicated because these systems have to talk to each other, so the geoid and the ellipsoid have to know where each other are. The other thing I should mention is that the geoid is used for intercontinental ballistic missiles. If you want to have a missile attack, atomic attack, back and forth, they all use the geoid. None of the ballistic missiles use the ellipsoid. So this is you can think of as a civilian military system, and this is pretty much exclusively a military system, although some civilian airliners do use INSs as a backup. Velocity. So again, velocity is a bunch of velocities that we covered, so let's nail them down. Velocity in GPS is ground reference to what? The ellipsoid. The GPS will tell you what your velocity is relative to the ellipsoid, so it's a ground reference velocity, but it's reference to the ellipsoid. The INS will tell you also ground speed. It'll tell you ground reference relative to the geoid. So both of the velocities that come from aircraft sensors are ground reference, but the aircraft has a third one. The third one comes from the pitot system. The pitot system is that little tube that's out in front, measures the air pressure, and it goes into what's called the air data computer, or sometimes just right into a gauge in your cockpit. And it gives you the air pressure coming in. And that gives you what's called the true airspeed. The true airspeed is the negative of the relative wind, And of course that defines the angle of attack, right, as we did in class. So the angle of attack is not defined by ground speed, but it is defined by the true airspeed, and that's why you need a pedostatic system on your airplane. Now, how is the ground speed and the airspeed related? Well, they're related by the atmospheric wind velocity. And actually, if you have a GPS and an INS on your aircraft, you can solve for the wind, and you can tell the ground station what the wind is for your airplane. They do that all the time. If you're flying an airplane that has GPS and INS, then you can call the weather station and tell them what the wind is where you're flying, right? Otherwise they'd have to send the weather balloon up there to find out what it is. So this is done all the time. That's the relationship between airspeed and ground speed. The final thing we talked about is time, and this gets a little bit complicated as well. So we have GPS time that has absolute dependence on the vibration of the cesium atom. We'll go into that in week 9. But what you have to remember is that that GPS time never stops, never skips, never leaps. It just keeps going. It just keeps going. And that's what we use. That's now become a time that everyone uses, a very popular time. Truck drivers, aircraft people, flight tests, everybody uses. You do, your watch, your cell phone, it's all using this GPS time based on cesium. There's also a time that we used to use, and that is used to, it actually can be used for sextants and sightings of the stars or for the sun, and that's Zulu or Greenwich Mean Time or Universal Coordinated Time. This is laboratory determined, and it's linked to the Earth's rotation and position. So we talked about this again last week. Sometimes every year the Earth's about a quarter of a day off, so you have a leap year every 4 years. And every day at noon, the sun is at a little bit different position at noontime. Right at 12 noon, the sun is just a little bit off. So as that error builds up, the Zulu time will skip a second. So every once in a while, you used to call them on an HF radio, you call WWV, and then they give you a beep, and that beep would skip, and you'd lose a second or you'd gain a second. And of course, the difference now between the second skips that keep the Earth in one position in space and the GPS is about 18 seconds now. Right now, it's about 18 seconds. When I started teaching this class, it was about 11 seconds. And that's over about 12, 15-year period of time. This is how they navigated in the Middle Ages. So they would take a time reading of high noon at Greenwich Mean Meridian in London. They'd drop a ball. They'd drop a ball at high noon in London. All the ships would be there, and they'd all set their clocks. These would be about 1780. And now we still drop the ball, don't we, on New Year's Eve? That comes from the English, what they used to do. They drop the ball. Then they take off on their ships. And then at noon, they might be, say they move over from London, they'd move over to be somewhere in the Pacific Ocean. They'd be somewhere in the Pacific Ocean out here. Well, they look at high noon, and then they look at the clock, and they see they're two hours off. They're 2 hours off from what it is in London. So then, because of the time difference and how they knowing how fast the Earth rotates, they know what their longitude is. And that's how Captain Cook navigated. That's how he navigated, found all the islands. He was the first one that had accurate clocks from a guy named John Harrison in England, who invented these clocks around 1780. And it was an amazing story, and that story is called Longitude, and I think you can watch it on Netflix, the story of how they used it. But that story about longitude would be a great teaching tool of how Zulu and GMT works, and why it's still with us. So the way I can explain this, when I was in pilot training, we had Germans in our class, young German officers, naval, and they were going to learn how to fly the F-104. At Williams Air Force Base, Arizona. So we thought, this is great, because our intramural soccer team is going to kick butt, right? We ended up losing all the soccer games. And I went up to Lutz, one of the pilots, and I said, what's the deal? You guys are from Europe. And he said, well, we're not athletes, we're pilots, So that kind of settled that. But they were really upset, because at the time, there was some 30-minute shows on. One was called Combat. I don't remember the other one. They were black and white, and they were typical, Nazis are bad, Americans are good, typical Saving Private Ryan every week for 30 minutes. And every Tuesday or Wednesday, whatever, the day after the show, they would come in, because they'd watch this show. And they'd say, how can you Americans watch this crap? It is so biased, it's so terrible. You know, and I remember I told Lutz, I said, well, you know, you guys win the next war, you can make your own videos of how it came out. But I guess what I'm trying to say is that we glamorize a lot of these things without putting them in perspective. And they do that to make a buck or to satisfy your archetype that we talked about last week, a heroic archetype that's in our culture. And sometimes this can be damaging, especially when you're related to war. Industrialized war and ethics are hard to justify. And we even see Snoopy in the Red Baron. When I was a kid, the number one song was Snoopy and the Red Baron. It was number one for about 8 weeks. Now you'd have to make a rap version of it to get popular, you know, to make it into the Grammys. But what we're finding is that war accelerates social progress, but we're not always sure that it accelerates our moral progress. In fact, sometimes it can become just terrifying as to where we're going with it. So here's Elon Musk, and he's a Walt Disney type of guy. Whatever is technically progress to Elon is progress. He's going to do it. We're going to go to Mars, and he's going to get everybody excited, and that's wonderful. And this is an actual picture of one of his cars he sent into space with, I guess that's the dummy that's in it. They're just showing how exciting technological progress it can be. And we're gonna kind of take a look at the history of that, going back from World War I, the history of it, and look at the aces, the exciting Battle of Britain, and then we'll decide who really killed the Red Baron. And the Red Baron, of course, was an aristocrat. First thing to remember is that the pilots in World War I were the ex-nobility, or the nobility, right? If you had to have money to fly an airplane, so you were an aristocrat if you wanted to be a pilot. Otherwise, you were a ground pounder like the rest of these poor guys in the trenches. So it was an aristocratic, aristocratic enterprise and experience, and of course, the Red Baron was a baron. He was an aristocratic. He got shut down a couple times. Once his airplane broke. We'll talk about a lot of those things that happened to him. These are some of the aircraft that we had. This was the British aircraft. It's called the Sopwith Camel. And the reason I got a new toy, so if I screw around, hopefully the aircraft on the Allied side, or the most victorious, it shot down 1,294 enemy aircraft. So it was our most, the British best aircraft. It's developed by the Sopwith Camel group, and let's see, where are the American aircraft that we? Well, there weren't any. Why weren't there any American aircraft fighting in World War I? Well, because the Wright brothers couldn't sell it. Remember, they couldn't sell it to the Army? The Army wanted to see a completed fighter from the Wright brothers, like these bicycle makers are going to be able to make a completed fighter and deliver it to the Army. Well, that's the Army mentality for you. So all these aircraft, remember the Wright brothers sold the rights to French. All these aircraft we're looking at are French and British aircraft who realized what the Wright brothers had done and took advantage of it. And they also put a machine gun in it. Now this is kind of interesting because the first guy to put a machine gun in it was a Frenchman, and he put a machine gun on top, then he put it shooting next to the propeller, but to keep it from hitting the propeller, he put a blade there. So any bullet that was heading for a propeller would get deflected off. And his name is Roland. But then the Germans took it, Guy Fokker took it, Anthony Fokker took it, and he made it synchronized. He built a gear off the camshaft of the engine that fired the machine gun so that the bullet went between them. So it's kind of interesting. We think of the Germans as inventing the synchronized machine gun, but it was actually a French invention. The Germans invented the synchronization.